Hi, this is Dr. Collins Jones. Welcome to segment 5 of my video series on measurement, significant figures, and basic data analysis. In this segment, we're going to cover volumetric measurements greater than 1 mil. Volumetric labware is used to accurately measure liquid volumes. Oftentimes people also refer to this as volumetric glassware, but because some of the volumetric labware is actually plastic, I'm just going to refer to it collectively as labware, volumetric labware. What's pictured here are some common volumetric labware items, right? And we're going to talk about each one a little bit in turn, and then in the subsequent slides, the ones that are important to the biotech lab will be discussed in more detail. So let's start with volumetric flasks, right? Volumetric flasks come in all different volumes, and they are designed to contain a specific single volume, and that volume is printed on the flask. So you can see here 100 mils, 500 mils, easily discerned, right? They have a ground glass stopper. One of the things that I want you to take note of here are these bottles that are tinted, right? So we use tinted volumetric flasks or tinted storage bottles if the chemical component, if one of the chemical components in our solution is light sensitive. So we use tinted labware, that is darkened labware, if one or more components in our solution is light sensitive. Next we have graduated cylinders, and again, they come in many different volumes. And so here we are ranging from 10 milliliters all the way up to 1,000 milliliters. In my lab, I actually have 2-liter and 4-liter graduated cylinders as well. They're not very accurate, but they are useful for preparing buffers that won't be used for quantitative purposes. This might be something like a running buffer for an STS page gel or a running buffer for a DNA agarose gel. Then we have pipettes, and there are really two main categories of pipettes that we encounter in chemistry, biology, and biotechnology. The first are these. These are serological pipettes, and these are designed to deliver variable volumes. So, for example, these are 1 and 2 mil pipettes, 5 mil pipette, 10 mil pipette, 25 mil, and so forth. If we just look at the 10 mil pipette, a 10 mil pipette could deliver 10 mils. It could deliver 8.5 mils. It could deliver 2.7 mils. So the serological pipettes are designed to deliver different volumes depending on what you need. The other type of pipette is referred to as a transfer pipette or a volumetric pipette. And much like a volumetric flask, these pipettes are designed to deliver a specific volume. And again, the volume is printed on the pipette. So the prominent one here is 100 mils. This pipette will deliver 100 mils. So you draw up to the calibration mark in the pipette, and then you let the liquid drain freely out, and 100 mils of liquid will drain out of this transfer or volumetric pipette. There will be liquid down in the tip, but the pipette is designed for that liquid to remain there, so you do not blow it out, you do not push it out. And then finally, we have burettes, right? And burettes, again, are designed to deliver very specific volumes, but in this case, the volume that we deliver can in fact be variable, and as I'm sure you know, burettes are used in titrations. So mostly in the chemistry lab, in our biotech labs, we do not use burettes. Okay. Occasionally, especially as you rise up in your job, you may be involved in purchasing and selecting volumetric labware. So here are some of the things that we want to consider. First is accuracy and precision. So accuracy, we'll cover this in one of the last segments in this series, but accuracy is how close the value is to the true standard or accepted value. So what we're really saying is, if I, for example, I'm going to use this graduated cylinder and I fill it to 90 milliliters, is that really 90 milliliters, right? Is this an accurate volume, or is it 89 mils or 91 mils, right? So that's the accuracy, right? And of course you're going to pay for that. And then precision would be if I buy several of these 100 mil graduated cylinders from the same manufacturer made on the same day in the same lot, and I fill each of those up to 90 mils, will each one be 90 mils, or will there be some variation between the graduated cylinders? Even though they're all designed to hold the same volumes, there might be a little bit of variation due to the manufacturing process. Maybe the diameter inside isn't exactly equal for each one of these. Maybe the calibration lines weren't printed exactly the same way. So precision is how close your values are to one another. Then we worry about mechanical strength. We don't want this to fall over. We worry about the temperature range. What range is this usable in? What if we need to, use heat to dissolve something? What if the liquid what if we're mixing two liquids together and it generates a heat of solvation, right? So we want to make sure that this glassware or labware can withstand different temperature ranges. Similarly, we worry about chemical resistance, okay? And so, what if I need to put acetone or methanol or some other organic solvent or even strong acid or strong base into this labware? Will it be able to withstand that? It won't be damaged by that addition. So one of the things that we think about is that increasingly we have a choice between purchasing glass labware and plastic labware, right? And so the nice thing about plastic labware is if you drop it, it doesn't break, but it does wear out over time, much more so than glass. The plastic eventually becomes brittle because the plasticizers leak out, and especially if you store the plastic in the presence of light, the plastic degrades a little bit faster. And plastic has a little more, some more challenges when it comes to chemical resistance. But plastic is cheaper, which brings us to our next point, cost. Okay, so a lot of times now you also have the choice between purchasing single-use or reusable labware, right? So single-use is designed to be used one time and then discarded, right? This is especially true if you are doing aseptic work, something like microbiology or cell culture, where the item needs to be sterile when you use it. And so you can buy individually wrapped single-use serological pipettes. You can even buy single wrapped graduated cylinders and so forth. So we have single use versus reusable. Of course, the question then comes up about sustainability, but you really have to think about this, right? So single use, yes, you're generating plastic waste. It's being thrown out. Right now, it is difficult to recycle plastic labware, use plastic labware, but that's a challenge for those of you who are listening to this to come up with a way to do that, right? If we have reusable labware, whether it's plastic or glass, that means that you have to use water to wash it. You have to use lots of water to wash it because you need to make sure that you've rinsed away any of the cleaning agent so that it won't contaminate whatever you're doing next with this piece of reusable labware. And oftentimes you'll also wash this with hot water, so you're taking a lot of energy. So, there's not a good answer when it comes to complete sustainability, but it is a challenge for you all to think about. And then finally, readability, right? How easy is it to actually read the gradations, the calibration markings on the piece of volumetric labware that you're going to purchase? So that's something to think about. And it is easy to figure out what those gradations are, and we'll give you some examples in upcoming slides here. All right. Okay, we are going to cover in this segment volumetric flasks, graduated cylinders, and serological pipettes, because that is what we use most frequently in our biotechnology labs. Before we proceed, though, if you've ever looked at volumetric glassware, there's a lot of stuff printed on at the top of the glassware. There's a lot of information there. So I'd like to take just a few minutes and explain to you what some of these letters and numbers mean. Okay, so first of all, we mentioned before that we might need to be concerned about accuracy. Are we really measuring out 90 mils in this case? Are we measuring out 50 or 40 mils in this graduated cylinder? So this first piece of labware is a graduated cylinder, and this is a burette. okay? At least just part of a burette, because I just wanted to show all the different labels on here. So the first thing that we have is we have a classification of the labware based on how accurate it is, right? So Class A labware has the highest level of accuracy. It's supposed to be made of borosilicate glass. And then Class B is not quite as accurate as Class A, and it's made of soda lime glass. So obviously the Class Bs, because they're not as accurate, they're made of a cheaper grade of glass, they cost less, all right? The next thing that I want to bring your attention to is the idea, the concept of TC versus TD and the calibration temperature, right? So TC means to contain. So if you have TC printed on the labware, that means that it's designed to contain that volume, okay? So when you fill it up to the calibration mark, it is containing 100 mils if it's a volumetric flask. When you pour the liquid out, it is not going to deliver 100 mils. A few droplets will remain behind in that glassware and that labware. So again, it's designed to contain that volume, but it doesn't deliver it, right? But this is used to make solutions very accurately, usually used to make standard solutions where we know the exact concentration, so we have to have an exact volume, right? Then we have TD, and TD means to deliver. So this is designed that when you drain it out, even if there's a droplet left behind, it has delivered exactly that volume. So that's what we see, for example, in the transfer pipettes or the volumetric pipettes, right? So those are designed to deliver 100 mils. You fill it up to the mark, you let it drain out, and the liquid drains through the bottom, and it appears to be a drop or two of liquid in the tip, but that piece of labware has been designed to account for the fact that not every bit of liquid is going to drain out. Now, some companies and in some countries, instead of TC, they use IN, right? They use the initials IN. So IN and TC mean the same thing, to contain. And instead of TD, companies and countries use EX. So EX and TD are the same thing. And so you can see those here, right? This particular labware is marked with the IN and the EX convention. Okay, then you notice on here that there are actually temperatures printed, in this case 20 degrees centigrade. This is the temperature at which this labware is the most accurate. In other words, it was calibrated at a temperature of 20 degrees C. So technically, if we're at 25 degrees C, room temperature, if we're at 25 degrees C, then this is not completely accurate, right? For the most part, in academic and research labs, we acknowledge that there's a temperature factor involved here, but we generally ignore it, okay? However, I've been to one or two companies where they actually have temperature controlled rooms that are dedicated to the preparation of solutions. And so in that case, all of the labware is put in the room, the solvent is put in the room, and all the solutes are also put in the room for 24 to 48 hours. So they are all at the same temperature, and that is, if you're using labware calibrated at 20 degrees C, then everything will be 20 degrees C when you use it. Okay, so that's what the temperature means. And then you may see precision, right? Plus or minus 0.50 mils or plus or minus 0.1 mils. So this is the precision of this particular volumetric labware. And again, we're going to talk about accuracy and precision in one of the last segments in this series of videos. But this just tells you that this is going to be accurate, right, to plus or minus 0.5 mils. So as you use different graduated cylinders, even though it's manufactured by the same company, right, the readings could be off by 0.5 mils. Could be up to 0.5 mils more or 0.5 mils less. And then here, the burette, which you're paying for a higher level of accuracy, even though it's Class B, right, the precision here is plus or minus 0.1 mils. And so if it was a Class A burette, the precision might be plus or minus 0.05 mils. And so you have to decide what level of accuracy and precision do you need when you're purchasing this type of labware. And then finally, you may notice ISO. So ISO stands for the International Organization for Standardization, right? And then some people call it the International Standards Organization, which makes more sense with the initials. But if you look this up on the internet, they actually list ISO as being International Organization for Standardization. So this is yet another organization like NIST, right, or the ASTM that we talked about in preceding segments, that really focuses on quality and making sure that things are accurate and that every manufacturer meets the same standards so that our measurements are comparable across the board. And then the numbers that you see here, 4788 and 385. 4788 are the specifications, are the standards created by ISO for graduated cylinders, and 385 refers to the standards created by ISO for burettes. And so they have little documents. You can look this up, and it tells you all the important things that you need to consider in the manufacture and sale of any kind of labware. So there's also an ISO number for volumetric flasks, for transfer pipettes, and so forth. Okay. All right. And so other examples of labware, I just want you again to see the printouts. But here I found a transfer pipette which has the TD, right, designation instead of the EX. And here in the volumetric flask we have TC designation, but you can see we have the other things here, 20 degrees. Look, this is kind of interesting. Here, the calibration was done at 27 degrees instead of the more normal 20 degrees, right? And then also this is certified by the ASTM instead of ISO. So again, these are all things that you sort of want to consider, and you can see, again, we talk about the precision. This is plus or minus 0.03. Plus or minus 0.0, I can't really read that too well, but it looks like 8 to me. And here's plus or minus 0.08 again, okay? All right, now, another thing that we need to consider when we're making volumetric measurements is the effect of the meniscus. So the meniscus is the curve that occurs at the surface of a liquid when that liquid is in contact with a different surface or different material. And this results in surface tension. And here what we really mean, the different material, is the glass or the plastic in the volumetric labware. That is, it's the walls of the vessel, of the container that the liquid is in. And so what that results in is this curvature of the liquid known as the meniscus, okay? And so this curvature arises from surface tension, which is a balance between cohesive forces and adhesive forces. And basically, without reading this to you, the cohesive forces are the intermolecular interactions between the molecules of the liquid. They're all being attracted to each other. The liquid is trying to be pulled into as small volume as possible. But the adhesive forces are the intermolecular interactions between the molecules of the liquid and the atoms or molecules in the walls of the container or the vessel that the liquid is in. And so you can sort of look at this. These are two different forces, and together they create this curvature or meniscus in the liquid. Okay? Different liquids have different curvature. So water, the meniscus curves down. All right? So in water, the meniscus curves down. And to make sure that everybody reads any aqueous, right, solution, that is a solution in which water is a solvent, to make sure that everybody reads aqueous solutions the same way, by convention, everyone agrees to read the bottom or the minimum point of the meniscus when we have an aqueous solution, that is a solution in which water is the solvent. Alcohol has no meniscus. There's no real surface tension when we have alcohol solutions. And so this is an easy one because the surface is flat. And that's why, as we mentioned in a previous segment, we like alcohol thermometers because, one, they're easier to read since there's no meniscus, and of course alcohol is safer than mercury to use. And speaking of mercury, the meniscus for mercury actually is upwards. So it's an upwards meniscus. And so again, by convention, if any of the liquids that we're trying to make a volumetric measurement with have surface tension that creates the meniscus going up instead of down, then we read the maximum or the top of the meniscus. Okay, and so here we have the meniscus is what? Facing down, right? Concave down. So we're going to read the minimum point, the bottom of the meniscus. All right. What we're going to do now for most of the rest of this segment is focus on those three specific pieces of labware that we use most often in the biotech lab to measure volumes. So we'll start with volumetric flasks. Volumetric flasks are designed to contain, that is their TC or IN, a specific volume of liquid at a specific temperature, right? And so you can see that here, right? Here we have the calibration. This is the fill line. And so this is a 250 mil volumetric flask, right, with a precision of plus or minus 0.12 mils. And so when we fill this with liquid up to this line exactly, then it contains, right, TC, it contains exactly 250 mils if the temperature is 20 degrees C. And again, in most cases, we ignore that temperature specification, but I just sort of want you to be aware of it, right? And you can see that this is Class A. Are you guys picking all this up? This is Class A, so it's very accurate. And we can't tell who the certifying body is. It's not turned enough to say whether it's ISO or NIST or ASTM or some other certifying body, okay? So the correct volume is achieved when the bottom of the meniscus is exactly even with the calibration line. So in order to achieve this, once you fill the volumetric flask up into the neck like this, and maybe it's about here, then usually what people do is they take a dropper and they add the last bit of solvent dropwise until the meniscus is just level. The bottom of the meniscus, if it's an aqueous solution, is just level with the calibration line. Now, one thing that's really important when you're preparing solutions like this is all of the solutes must be completely dissolved before you bring this to the final volume here, before you actually make the meniscus even with the calibration line. So again, all the solvents must be completely dissolved before you bring this to the final volume, because on dissolution, dissolving the solutes can sometimes change the volume, okay? If the volume exceeds the calibration line, if you add too much, and we'll give you some illustrations of that in a minute or two, then this is incorrect and you need to start over again, all right? There are several different kinds of cap formats. Here we have a ground glass stopper, right? And this is called a penny cap, because what you can do with this cap is, and I don't see these as much anymore, but in the old days, what you would do is you would take your hand upside down and put your fingers in between the cap, lift it out, and then if you turn it over, your palm is free to grasp this volumetric flask, all right? But we also have plastic stoppers and snap caps. So mixing is accomplished by holding the cap firmly in place and completely inverting this volumetric flask a minimum of 15 to 20 times. By inverting, we mean turning it completely upside down and then right side up, upside down, right side up, so that the liquid in the top flows past the liquid in the bottom and vice versa. This is the best way to ensure complete mixing. If you don't believe me, try this at home. If you have salad dressing that has separated into two phases, like if you have oil and vinegar or something like that, if you mix by inversion instead of just shaking upright, you'll get a much better mixing and your salad dressing will taste a lot better. You obviously, hopefully it's obvious, you should not put a stir bar in a volumetric flask, because the stir bar has a volume. It will displace some of the solvent and that will make the volume incorrect, right? Volumetric flasks are often used to prepare standard solutions. Remember, a standard solution is a solution whose concentration and composition is known exactly. Okay, so just let's look at what can go wrong here. Here, in this case, the volumetric flask is underfilled. We can remedy that by just adding dropwise the rest of the solvent until we actually have the meniscus level with the calibration line. Okay, so that's repairable. Here's the calibration line, and you can see that we have overfilled the volumetric flask, right? You can't just remove the extra liquid because you notice, right, that the solute, which is yellow, is now part of this liquid. So if we would just remove liquid to get back level with the calibration line, we've changed the concentration. So if you overfill, you have to remake the solution. You have to start from scratch again with a clean, dry volumetric flask, because if there's any droplets of this liquid in here, that will affect the concentration of the solution that you're trying to make. Okay, so what does it look like when you do it right? Here you go, right? Here's our volumetric flask, right? And here's our calibration line, and the meniscus is exactly even with the calibration line. So this is correctly filled, and we're happy. Yay. Okay. Next, graduated cylinders. Graduated cylinders are used to measure a liquid volume when total accuracy is not essential. So a graduated cylinder is not as accurate as a volumetric flask or a transfer pipette. But the trade-off is, while it's not as accurate, I can measure different volumes in the same graduated cylinders. And this is important, and we're going to emphasize this at the end of this segment. Graduated cylinders are more accurate than beakers, Erlenmeyer flasks, bottles, but they are not as accurate as a volumetric flask or a pipette. They are generally faster to use to measure and deliver specific volumes. Okay, there are A and B standards, right, for graduated cylinders, and again, A is more accurate, and you can see here A and B, right? So this tells us the relative accuracy. This is a more accurate graduated cylinder than this. Okay, measuring graduated cylinders generally have a pour spout right here, and you can see that on at least two of these graduated cylinders we've put little plastic guards here. These are especially good for glass graduated cylinders because if you knock it over, the guard prevents the whole body of the graduated cylinder from hitting the countertop, and so it won't break. If you drop it on the floor, it's going to break. But if you just happen to accidentally knock this over, this kind of like catches the graduated cylinder and prevents it from breaking. These two graduated cylinders are referred to as mixing graduated cylinders. So here, these actually have firmly fitting stoppers so that they won't leak, and so you can mix things by inversion in this. I actually used to be, in my early days, a lipid chemist, so I would be extracting phospholipids and cholesterol, and this is exactly what we used. We used these ground glass mixing graduated cylinders because you wanted to have a certain ratio of organic solvents to water, and then you put your sample in there, inverted it up and down, and the lipids partitioned into either the aqueous phase, the water phase, or the organic phase, and the phases would separate in there. But it was nice to have this cylinder because you could see exactly what volumes you were dealing with. Okay, now I have found that oftentimes students have difficulty reading graduated cylinders, and honestly sometimes I have to sit down and look at the graduations, the calibration markings on the cylinder to make sure that I am reading it right. So let's just discuss how to make readings on a graduated cylinder for a few slides here. All right, so here's our graduated cylinder. We have our meniscus, and you remember that we're always going to read the minimum of the meniscus. When you are looking at a liquid, right, there's something called parallax error. And so parallax error is just when you're not looking at this straight on, you're looking at an angle. So whenever you're reading the graduated cylinder, you want to look from a straight perspective, a linear perspective, a straight line, okay? But you only do this after you've filled the graduated cylinder. Don't be bending down with the graduated cylinder at eye level while you're pouring liquid into it because it could splash out and hit you, right? And I know that you'll be wearing safety goggles or safety glasses, but you still could get something on the rest of your skin, which could be dangerous. So you fill the graduated cylinder to the volume, and then you make the reading, okay? And if you need to add a little more, you add a little more. And in this case, if you need to pour a little out, you can pour a little out. But parallax error is when you're looking at this from above. You can't do that. Or you're looking at it from below the meniscus. You can't do that. So again, make sure that you're looking at this head on in a straight linear observation. Okay, and again, we read the minimum of the meniscus. All right, so here's an example of a graduated cylinder. And again, this is one where you have to take a minute, at least from my perspective, to look at how this is calibrated, how the volumes are gradated on here, all right? So we have 6 and 8, okay? We have 6 and 8. So this line that goes all the way around is 6 mils, and they've printed the volume of 6 mils above the line, okay? And then this is 7 mils, and it doesn't go all the way around. And then we have 8 mils, which does go all the way around. So now if you count between the 6 and the 7, you'll see there's 4 graduations. So that means that these have to be by 2. So the first one is, again, 6.2, then 6.4, then 6.6, and then 6.8, okay? And then this would be 7.2, 7.4, 7.6, 7.8, and so forth, okay? But you have to take a minute to really see what these calibration marks mean. Okay, so again, the meniscus is downwards, so we're going to read the minimum of the meniscus and see where that goes. And to me, this looks like it's 6.60. And honestly, I'm not really sure if you can call that 6.60 because the next one is 6.8, right? And so somewhere in between there is 6.7. So this is really, this 6.60 is really uncertain. The 0 is uncertain for sure, okay? But I'm calling it 6.60, and that means there's 3 significant figures. All right, if we look at this, we're going from 50 to 60, and we can see that there are 9 graduations in here. So let's just sort of look at this. So this is going to be 51, 52, 53, and the next one will be 54, and then 55 and so forth. But the meniscus is between 52 and 53, and it looks to me like maybe it's a little closer to 53. So I'm going to call this 52.7 mils. And again, this is where the uncertainty comes in, because a different observer could look at this, and maybe you looked at this and said it's 52.8 or 52.9 or maybe even 52.6. So that's where the uncertainty comes into measurement, the estimate. You are making the estimate of the 0.7. But again, this is 3 significant figures. Okay, so hopefully you're getting an idea of how to read the calibration scales on a graduated cylinder, and it's very similar for serological pipettes. So I won't spend the same amount of time with the serological pipettes. All right, so it's your turn. Practice reading these and see what you come up with. And I'm going to do my normal count to 3 to 5 and pause, and then you can pause the video and see if you can record the correct volumes and maybe even think about the number of significant figures. Okay, I'm back. What'd you get? For this one, I got 25.8, right, mils. And remember, we have to include the units. It's not a measurement if we don't include the unit. And that would be 3 significant figures. Here, I'm going to have 6.32. And again, this is, that 2 is uncertain, and that's going to be estimated. And again, 3 significant figures. Our uncertain digit from my recording is 2. If you read this as 6.33, then your uncertain digit would be 3. If you read this as 6.31, then your uncertain digit would be 1. Okay, here I'm reading 74.2 mils. Again, 3 significant figures. And again, the uncertain digit is 2. And then this one, right, I'm kind of happy I found this particular example, but this is not a graduated cylinder I would purchase for use in the lab, because I really don't like the way that this is calibrated, that we have the gradations marked here. So if you look at this, there's our 5 mils, okay? That's going to be 5.5 mils, and then this will be 6 mils, right? And so you have to count the number of lines in between and figure out what they correspond to. But this is calibrated in 0.5 mils. So we started with 5 mils, 5.5. So the next small line, short line, is going to be 6.5, then 7, and then 7.5. And hopefully that's enough to give you the pattern of how we read these calibration lines. So if we go up, all right, and there's 8. So if we go up, there's 10, okay? There's 11, right? And the one in between 10 and 11, it's 10.5. And so it looks to me like at 11.5 is where the meniscus lies. So this is going to be 11.5 mils, 3 significant figures, and the uncertain digit is 5. All right, but wait, there's more. I have a whole page here of practice volumetric readings to make. So let's start by determining and recording the volume in each of these graduated cylinders. I'm going to count to 5 again to give you time to pause the video and then write down what you have read the volumes to be. Okay. All right, I'm back. So I'm just going to fill these in. I'm not going to explain how to do each volume, but let's just see what you came up with. First one, 440, 7.0, 249, 37.0, 19.9, 189, 86, 35, 280 mils, and 19.0 mils. Okay, so hopefully you got that. Now, let's indicate the number of significant figures in each volume measurement. So 3, 2, 3, 3, 3, 3, 2, 2, 3, and 3. Okay? All right. And then you know what the last one is, right? Write down the uncertain digit associated with each of these. So 0, 0, 9, 0, 9, 9, 6, 5, 0, and 0. All right. So hopefully this has enabled you to be able to have some confidence in reading graduated cylinders and also in identifying the number of significant figures and the uncertain digit. And in the next segment, we're really going to lay out all the rules for determining which digits are significant and which is the uncertain digit. But first, we need to go to serological pipettes. So pipettes are generally used to transfer liquid volumes between 2 mils and 25 mils, but they can also be used for 50 or 100 mils. So there are serological pipettes that are capable of holding and delivering 50 mils or 100 mils. We don't use those in our lab because with that much volume in the pipette, the weight is so great that we tend to have dripping out of the bottom. And if you use the electronic pipette aid, you have to be very careful to always keep the suction going. You have to just gently depress the button that draws up to keep enough suction so that the liquid doesn't drop out. But it's way too easy to draw things up into the tip and into the into the electronic pipette aid. So we don't pipette more than 25 mils. If we go above 25 mils, we use a graduated cylinder. Okay? So there are different types of pipettes, right? We're focusing on serological pipettes or more pipettes, right? And there's just a difference in where the volume is. And I've just included volumetric pipettes here in order to be complete, right? So serological pipettes or more pipettes are measuring pipettes that can deliver different volumes. And again, the volumetric pipettes, these are transfer pipettes designed to deliver a single fixed volume. Okay? So in biotech, we primarily use serological or more pipettes. And so if we look here at the tips, we said before, right, this is a 10 mil volumetric pipette right here. This is a 10 mil volumetric pipette. When you let this drain freely, there's going to be a little bit of liquid left in the tip here, and that is by design. So you just leave it there. You don't push it out. It's designed to drain and leave a little bit of liquid behind. Now what I want you to notice here is that in a Moore pipette, we're going to go from 0 to 10 mils, but then there's a space here. So there will be liquid here, but this liquid is not part of the measurement, right? It stops here at 10. And then in a serological pipette, this is 0 to 9, and then from 9 to the bottom of the tip is the last mil. So in the serological pipette, you would actually blow this volume out to deliver the full 10 mils. But in the Moore pipette, you would not. Okay? And so again, just to sort of illustrate this, I'm going to just focus on the calibrations, whether it stops before the end of the tip or whether it kind of continues all the way to the end of the tip. You have to take note of that. All right? And same thing here. Right? Different calibrations. So here we would leave this liquid in because this is 5 and it stops at 5. But here we will blow it all the way out. And so how do you know? Well, it turns out the manufacturers have actually put rings around the top of the pipette. And so if there's one ring, this is a to deliver, you just allow it to flow out and you leave the liquid in the tip. You do not blow out. You do not use your electronic pipette aid to push out that last drop of liquid if there's a single ring on the top. Serological pipettes will have 2 rings, all right? And in 2 rings, then, if you want to deliver the full volume of the pipette, 10 mils, you have to blow out that last bit of liquid, all right? Oftentimes, we don't deliver the full volumes. We may use a 10 mil serological pipette to deliver 8 mils, okay? If we're cheap, though, and we just suck 8 mils up into the serological pipette, then you have to blow out that last drop. And notice all of these serological pipettes have 2 rings. And the other thing to sort of point out, it may be a little difficult to see, but each of these has a different color of the rings, and the color helps to indicate what the volume is. So there's way, besides just reading the volume, the color of the rings help to indicate the volume. So it's 2 ways to double check yourself to make sure you've chosen the proper volume of serological pipette. Okay, so reading a serological pipette and filling to deliver a specific volume. So here we have a 5 mil serological pipette. All of these pipettes, by the way, have 2 rings, so that means these are going to be blowout. And you can see that the calibration, even though, for example, this is a 5 mil pipette, it stops at 4, and the last milliliter number 5, is going to be contained in this space. This is a 10 mil serological pipette, and wow, look at this. This stops at 8 mils, so in this space, this volume will be actually 2 mils. And then here we have a 25 mil serological pipette, and look, 21 mils, so down here is 4 mils of liquid volume. Okay, so suppose we wanted to deliver 2.5 mils. There's a couple of ways you could do this, right? You could fill this all the way up to the 0 point, right? And then expel 2.5 mils, right? And that would leave 2.5 mils in the pipette. And the problem with that is I find that wasteful because you cannot put a solution back into the bottle that you removed it from because you risk contamination, okay? So the other way that you could consider doing this is you could fill this to 2.5 mils and expel, because 5, the total volume of the pipette, minus 2.5, the volume we want to deliver, equals 2.5. So we just fill it up to there, right? And then we just expel this, but we have to blow out the last drop, all right? We have to get everything out of the tip. So let's think about this for 10 mils. Suppose I want you to deliver 8.5 mils, right? 10 minus 8.5 gives us 1.5 mils. So we would fill this to the 1.5 mil mark, all right? As close as I can get with this arrow. And then we would expel this out. And again, this is a blowout, right? Because it's the double ring. And then finally, probably not my best example, but I'm saying deliver 14.8 mils from this 25 mil pipette. So 25.0 minus 14.8 gives us 10.2, and that's really nice. But, and this is where you have to think ahead when you do your lab work, and that's partly why I left this example in as it is if you notice, right, this is 21, 20, 19, and so forth, right? But there's only one line in between, so these are 0.5 mils. There's not 0.1, 0.2, 0.3, 0.4. So we're really not going to be able to accurately, we're not really going to be able to accurately measure 10.2 mils, right? We could do 10.5, but then it's going to be a guess between the 10 and the 0.5. So just keep that in mind when you're selecting your serological pipette to measure. And then you're just going to expel this, right? And again, it's blowout because there's two rings. All right, finally, last slide, right? I just want to reinforce, because we get this a lot of times from lab managers or companies, from people who haven't been trained in their whatever program they've been in. The calibration markings on a beaker, an Eldermeyer flask, a media bottle, or centrifuge are not accurate. They are only approximations. They are sort of like a courtesy put there by the manufacturer to let you get an idea as if you're close to the volume that you want. But these are not accurate volumes. These are simply containers designed to hold, to transport, or to mix, but they are not made for volumetric measurements. And so these can be off by as much as 10 to 20%, okay? So here, for example, this 400 mils, this really could be 380 mils. This could be, 410 mils. This calibration is not accurate. So if you were to take a graduated cylinder, measure out 400 mils and pour it into this bottle, and it doesn't, and that volume that you've poured in from the graduated cylinder does not exactly correspond to the 400 calibration line here, the graduated cylinder is the correct volume. This is the incorrect volume. So never use any of these to accurately measure a volume. Don't do it. Okay. Instead, use official volumetric glassware and everybody will be happy. And that is the end of segment 5.